Hello, ladies and gentlemen. Right now we're going to talk about a ball being thrown up into the air. Okay? Let's go over this example here. Again, I'm going to read the example to you and you can follow along and we'll all be on the same page for this. So, a ball is thrown vertically upward with a speed of 25.0 meters per second, which sounds vaguely familiar. A, how high does it rise? Not what we were asked before. B, how long does it take to reach the highest point? Alright, C, what is its speed when it returns to the level from which it started? We got an idea about that, but we need to make sure. And D, how long does it take to hit the ground from its starting point? Okay, so here we go. Ball being thrown straight up in the air. Oh, that was almost good. Alright, ball's thrown straight up in the air, comes straight back down. So we're going to diagram that. This ball, straight up in the air, comes straight back down. We'll assume all of the assumptions we made before. We know we want upward to be the positive y direction, downward will be the negative y direction. We'll start y naught as 0 because I don't see why we would do it any other way, right? V naught is again 25.0 meters per second, and again I wrote it a little too close to the line. Okay, and the acceleration due to gravity is negative 9.0 meters per second squared. All things that we know. Now, like I said, we have an idea of what we're being asked for. When it says A, how high does it rise? We're looking for that at the very top of its motion. This is the first thing we're looking for. That's our y value that we're looking for. Now, before we move on, we actually know something about this point. We've seen this earlier, how at that point, at the very top of its motion, the ball is at rest. It is not moving at all. We saw that because we know that the velocity here is positive and the velocity here is negative. In order for it to go from positive to negative, it has to go through 0. The ball moving upwards has to stop just for an instant where the snap of my finger is too long for it. But the ball goes up and stops and comes back down. Now that's another key that actually makes it fairly easy to work with these problems. Because I can say the velocity at this point, at the top, is 0. That's another value that I know. So the velocity is 0. Right at the very top, and then it starts to become very negative again on the way down. Okay? Now, what we've seen before is that this apex, if you will, is right between 30, so a little more than 30 meters. So we should be looking for an answer like that. How long does it take to reach the highest point? Well, we saw that was between 2 and 3 seconds, so we're looking for a number somewhere in there. What is its speed when it returns to the level from where it started? We've got an idea that it's 25.0 meters per second. That stands to reason based off of what we've seen before, but we need to actually verify that. We need to say without a doubt, yes, it's going to be 25.0 meters per second. Alright, first things first, let's look at A. How high does it rise? Okay, in this case, we do not have a time involved yet, so we've got to look through our look through our equations and find one that involves an initial velocity, an acceleration, and a final velocity, because we're really only interested in the trip from here to here at this point. Okay? Meaning that we know the final velocity. Okay? So the equation that we're going to use for this, for part A, is, wow. Nicely enough, we know that there are parts of this that are equal to 0 already, such as the final velocity at the very top of its trajectory. And y naught is also 0. So at this point we're left with 0 equals v naught squared plus 2g y being what we're looking for here. I'm going to solve this for y, subtracting v naught squared from both sides. So negative v naught squared is equal to 2g times y. We divide both sides by 2g at this point. Get just the position on its own, just its y position. Going to another board here, that's going to be y equals negative. Now you might look at this and say, wait a minute, we've got a negative value there, but remember that g in this reference frame with down is the negative direction. G is going to be negative, and then we'll take care of it and we'll get a positive value for the displacement, no matter what the velocity is. Okay? But we know what those things are, so let's just substitute those values in. Y is equal to negative of 0 meters per second. So this position at its highest point is going to be about 31.9 meters. Which is, as we predicted, we said from our last problem that it should be a little bit more than 30 meters up, and that is just what we get here. Okay? So, the important part of that is using the apex as sort of cutting it off halfway there. Alright? And seeing that we can use that value as 0 as we see fit. Okay? The next question, how long does it take to reach the highest point? Well, now we can use this value if we want to in our next calculations. Alright, that 3.19 value there. Okay? Again, don't use a complicated equation when an easy one will do. Alright, so for this one here, we can just use v naught plus gt. Very similar to something we've done before, okay? But now, we know both of these values. We know g. We're looking for t this time instead of v, alright? Again, if we are just going as far as the top of the motion, v is still equal to 0 at this point. So we've got 0 v naught plus gt, and then solving this for t minus v naught. Divide both sides by g. We end up with t is equal to negative v naught over g. Again, the negative value for the acceleration due to gravity is going to make this a positive value in the end, which is what we should expect for a time, right? Putting some numbers into there, you will find that you're getting about 2.55 seconds. .55 seconds, which again meshes with what we knew before. We knew that at 2 seconds it's right about here, and then at 3 seconds it's right about there. So it has to be at the apex of its motion somewhere between 2 and 3 seconds. Part C. What is its speed when it returns to the ground? Like I said, we've already got this idea that its speed when it returns to the ground is about 25 meters per second. Well, we could say the velocity when it hits the ground is maybe 25.0 meters per second. But like I said, we have to show that that is true. We have to verify that. Okay? So we're going to do some algebra for that. And we're going to see, okay, well, if I want to get to the ground here, I've got an initial velocity. I'm going to look for the final velocity at the ground. We're not really worried about the apex anymore, so we can't use v equals 0. It's not 0, it's whatever it is down here. That is what we're looking for. So we know an initial velocity, we know an acceleration, and we know an initial position. And this is what is really going to help us out here, this initial position. Okay? Because if we know the initial position and it returns back to its initial position when it hits the ground again, or from which it started, we know that the final position is 0 as well. If that is true, then we know initial position, final position, an initial velocity, and an acceleration. And we've got an equation that handles all of those things and will also tell us a final velocity. So we can use this equation again, right? Knowing v naught, g, y, and y naught, we can put all of those into it. So we'll see right away that y minus y naught is going to be 0, and if this part of it is 0, 0 times 2g is also 0, and we can see that v squared is equal to v naught squared. If we take the square root of both of these, we'll see that v is equal to, now we have to be careful here, because technically the square root of v naught is going to be positive or negative v. Alright, positive or negative v naught. Now, here's where the math, you have to understand the physics to interpret the math. Okay? Only one of these values makes sense. It's either the positive value or the negative value. Okay? Now the math tells us it could be either of those. The square root of any number is a positive and its opposite. Okay? But only one of those makes sense in this context. And in this context, we can see that at this point, the ball is going in which direction? The negative direction. If it's going in the negative direction, that means that our positive value for the square root here doesn't make sense in this context. We're going to say that v is equal to the opposite of v naught. And here we have a mathematical proof that when the object hits the ground, it's just going to have the negative value of whatever it started with. So if this object starts with positive 25.0 meters per second of velocity, it's going to go up and it's going to come back down, and when it hits the ground, it's going to be traveling at a speed of 25.0 meters per second. Notice how nothing in the path mattered. It doesn't matter how high it goes or how long it goes. It just matters if it goes, starts at this velocity, it will end with that same speed in the opposite direction. Okay. Also, we can see here, it's going to work for whatever speed we put into it. Whatever speed it leaves the ground with, it's going to end up with the negative of that when it returns back to the position that it started from. Okay? We can also see that, in a way, just so long as there is an acceleration due to gravity, it doesn't matter what that acceleration is. The acceleration on the moon is about 1/6 of Earth's gravitational acceleration, but it cancels out of our equation. It's not in our proof here. And so this means that if I launch this object at 25 meters per second upwards on the moon, when it comes back down to the surface of the moon and hits the surface of the moon, it will be traveling at 25.0 meters per second downwards towards the moon. It doesn't matter what the acceleration due to gravity is, it just matters that those two are equivalent.